Okay, we're going to try a significance test for a mean using raw data. Um, I'd like you to turn to section 9.3 and number 79 and try it out. Pause me now and give it a go. Okay, so here's how you did it. Hopefully you tried it out for yourself. First of all, as you're reading the problem, you should record kind of the key information. So here's what I had recorded. N is 20, our sample size. Alpha is 0.05. The null hypothesis value, this is what they were saying was kind of predicted or desired, was 11.5. And I had also underlined some key phrases. I underlined random sample, and I underlined differs from in the question, because the question is going to tell us about the alternative hypothesis and what sign we want there. All right, so with that key information, then we're ready to get started. So that's all just notes you would make to yourself as you're reading the problem. Now the rest of this is the work that you would show in your solution. First of all, we have to define the parameter. It's a means problem, so we've got mu is a mean, and this is the true average hardness of the tablets. They don't tell us what units that is, but that's fine for now. And so because we're doing a test for a mean, because our parameter is a mean and it's a yes-no question we're trying to answer, this is a significance test, so we will use a one sample t test. Remember, t goes with means, z goes with proportions most of the time. So our next step is to set up our hypotheses. Our null hypothesis, you can see up here, we had mu equals 11.5. So here we're going to have mu, the value we defined, the parameter we defined, equal to 11.5. And in our alternative hypothesis, because of the phrase differs from, that implies a not equal to. We need the same parameter and the same numerical value. Okay, so now we're ready to check our conditions. Continuing on, conditions. These are the same conditions we've been checking all along. Random, as we underlined, it was a random sample. Independent. So this is our 10% condition. So we've got 10 times n. So 10 times 20 is 200. And our population is bigger than this. There are presumably more than 200 tablets per batch. Because it was per batch that we were testing here. So the 10% condition is satisfied. And finally, normal. This is where it gets a little different. Remember that for means, we have three possible ways to check for normality. One is if we know that the population is normally distributed, but we're not told that in this case. That would have to be something that you were told or that you knew about this type of data. Another one is if your sample size is more than 30, you can use the central limit theorem. But we have a sample size of 20, not bigger than 30. So the third option is to graph the data and assess the relative symmetry or skewness and presence or lack of outliers to use the robustness of the t procedures. So hopefully along the way you had entered your data into your list. And so now we can create a graph of the data. Okay, it looks like we've got that on, so zoom stopped. And you want to trace along to see where your key values are. And you want to be sure to copy this plot onto your work with labels. So here's what I got. Oops. Here's a box plot of the data. You don't have to do quite as many markings as these, but notice that I spaced my scale evenly, even though my key locations are not going to be evenly spaced. And this is hardness. So be sure that your graphs, this is a nice reminder of some old material, to be sure that your graphs are very well labeled. And up to a little over 11.7. So you want to sketch the graph on and make sure you include a scale. So now we're going to analyze this for symmetry and skewness. The plot is roughly symmetric, maybe a tiny bit right skewed, but nothing very dramatic. And for a sample size of 20, which is getting up there close to 30, that's not so bad. With no extreme outliers, actually no outliers at all. It's important that you use the type of box plot that can show outliers if there are some. So since the T procedures, tests, and confidence intervals are robust, we can consider the sampling distribution of X bar approximately normal. Okay, so we've met all three of our conditions, random, independent, and normal. We can go on to the calculations. For a t-test, you're going to need a t-test statistic with degrees of freedom to get a p-value. And I recommend doing this on the calculator when possible. So, t, first you want to set up your formula. It's going to be our cutoff, which is our x bar from our sample, minus our null hypothesis value over the standard deviation for means, the standard error, s over square root of n. And so now there's a nice little cheat. Rather than calculate it, not cheat really, but just a shortcut. Rather than calculating each of those individually, you can go and carry out the test. So you're going to go to your test menu, do a t-test, number 2. Now we have the raw data here, so I'm going to keep it on data. If I had just the summary statistics given to me, I would go to that. So we're going to do that. Our null hypothesis value is 11.5. We're using data in list 1. We're doing a two-tailed test. So calculate. Now I can fill in, from that, I can fill in the t statistic, the p-value, x bar, and s sub x into my formula. So into my formula, my mean is 11.516. 11.5 was my null hypothesis value. Standard deviation approximately 0.095, 20. is my sample size. Again, I'm rounding a little bit here just for showing work, but I'm giving the more precise t statistic that was calculated, 0.772. And I know that my degrees of freedom are sample size minus 1, 20 minus 1 is 19. So what this means altogether is that for some t distribution with degrees of freedom equal to 19, wherever my mean is, the mean of the t distribution, this sample is a little less than 1 standard deviation away. It's 0.772 standard deviations away. And so my p-value is a combination of that and the tail, the symmetric tail on the other side. That little sketch helps you to kind of show that you understand what you're doing and also check to make sure everything makes sense. So the p-value, remember to label it as p-value even though the calculator shows it as p, is 0.449. So now we're ready to conclude. That p-value, 0.449, is a very big p-value. It's definitely bigger than 0.1 or 0.05, but we were using alpha equal to 0.05, and so we're going to compare with that. So since the p-value of 0.449 is greater than our alpha value, remember, if p is low, reject HO. P is definitely high here, not low. And so we fail to reject the null hypothesis. Then remember, after we do our comparison sentence and make the decision, you want to put it back into context. The question was asking if these pills have a hardness significantly different from 11.5. They do not. The pills do not significantly differ from 11.5 in hardness. That's actually a good thing in this case. A lot of times with scientific research, the researchers kind of want to be able to reject their null hypothesis to find something new and exciting. But in this case, they wanted a target of 11.5. So being right around 11.5 is a good thing for them in their average hardness. And that's a significance test for a mean.